So the Earth behaves as a magnet. In the northern hemisphere, in the geographic North Pole, it kind of behaves as a magnetic South Pole. And in the geographic South Pole, it behaves as a magnetic North. So now where are we? We are somewhere here, right? So if you take a magnetic needle and suspend it, if you take a magnetic needle, such as this, that's a magnetic needle, and suspend it here, just like that, so it's free to move. Which way will it point? It points in the direction of the magnetic field. Now, which way is the magnetic field? Now, you know about electric fields, right? It's very similar to that. Now this is a magnet, north, south. There are two ends. That is the front of the magnet, which we normally call as the North Pole. So that's the North Pole, and this is the South Pole. Now, around this magnet, there is a magnetic field. What's a magnetic field? It is a region where any other pole will experience a force. Just like, go through the same definitions as electric fields. What is electric field? Around a charge, it is a region where any other electric charge will experience a force. The same thing here. A magnetic field around a magnet is a region where any other magnetic pole will experience a force. Now, sometimes people call this North Pole as a magnetic positive magnetic charge, a magnetic charge, just to relate it to the electric fields. So they call this magnetic positive charge, and this is a magnetic negative charge. But actually, it's not a charge. Okay, so this is like a positive, and that is like a negative. So where are the fields going to start from? Positive and negative, where do the fields start off? Positive. The same thing applies here. So how do you understand the field strength? The same way as you understand the electric field strength. What is the definition of electric field strength? It is the force experienced by a unit positive charge when placed, right? The same thing goes here. Instead of unit positive charge, we call it unit North Pole. What do you mean by unit North Pole? It is a pole that has a strength of 1 unit. Now, we're not going too much into the magnetic fields and magnetism and all that altogether, but there is, every magnet has what is known as a magnetic moment. What is a moment? You know it. What's a magnet? What is a moment? Not the instant of time, the other one. What is a moment? Yeah. What's a moment of a force?
The magnitude.
Yeah, moment of force.
It's like the ability to induce magnetism.
No. Don't forget. Last year you talked about moment. The moment. You did a lab also. The moments. Principle of moments. Huh?
That sounds with inertia.
Yeah. Inertia is of course everywhere.
Momentum.
Not momentum, moment. One of the labs was titled Principle of Moments. Come on. He used a meter stick. Suspending a meter stick. What is that?
Gravity.
Is that with the simple equation?
No. It's not too far away. It was not too long ago. Moment is the turning effect of a force. No? I should retire. Yeah. Yes.
What is the vocabulary, like the word for pole? Strength of 1 unit. It's a unit pole.
A unit pole, yeah. Unit pole, strength of 1. You don't remember the experiment where you suspended a meter stick and put a weight over here and you found the mass of the meter stick and stuff like that?
Yeah.
Yeah, and made you draw all those things on the computer? Huh?
Yeah.
I remember that.
You remember that one? What is the principle of moments? Moment is a turning effect of a force. If you're going to use a wrench, you're pulling like that. So you're creating a torque. That's what it is. Torque is basically moment of a force, the turning ability of a force. So when you want to turn something, what you apply is not just a force, but a moment. So this thing has a moment, a turning ability. How come there's a turning ability? Because imagine there's a field like this. Imagine this thing is kept in a field. What will happen to this pole? It'll get pushed away from here. What will happen to this one? It'll get pulled in. So what will it create? A torque. It'll create a torque. So when I put this in a magnetic field, this will go that way, that will come this way, so it creates a torque, a turning effect. And there is a certain moment attached to it. You know, how much is the moment of that force, the turning effect. So if this thing is a very strong magnet, it'll have stronger poles, and so it will turn better. So there is a turning effect, and that is what is known as the moment of a magnet. So every magnet has got this moment, and also every magnet has got strength, and the strength is measured in terms of how strong is the front and how strong is the back. They call it pole strength. Okay, so those are terms we are not going to touch. We are not going into it because we are doing electromagnetism mainly. Magnetism, I'm just touching up with magnetism to give you an intro. Okay, but we are not going into the magnetization concepts or the pole strengths, or we're not going to really, work on magnet itself. So yeah, understand there's a pole strength. Understand this also has a pole strength. Now if the magnet is getting weak, the poles are getting weak. Okay. So as I said, this classroom behaves like a magnet. It's got a front and it's got a back. Now the stronger it gets magnetized, the front gets more aligned and the back also gets more aligned. Okay, the front and back gets more aligned, and so the front gets more strong, the back also is equally strong. Both go together. You normally don't have a magnet where the front alone is strong and the back is not strong. If the front is aligned properly, the back is automatically aligned also. Okay, so this is a magnet and it has a strength, and depending on the strength, it has its own field. So how do you know there's a field? Bring a unit north pole. You bring a unit north pole and place it here. Imagine, what is a unit north pole? I told you that poles don't come alone, right, in the last class? Poles don't come alone, they come in together. So how do you, how can you simulate a unit north pole, a pole that is like all by itself? No, it's not possible to get a north pole alone. But yes, you can almost get it if I have imagine a long metallic needle. And if I magnetize this long metallic needle, where is the north pole? Right there. Where's the south pole? Far away, all the way down, right? So if I'm focusing only on this and keep the magnet, so if I keep this magnet and put this thing right next to it, the other one is too far away to be taken into consideration. You understand that? And therefore, you can almost simulate that north pole effect. How you can simulate this? How can you do an experiment based on this? Let's say, suppose you take a water tub, you take your bathtub, put water in that tub, and make a magnet float. How do you make a magnet float? Or how do you put a magnet on the surface? I know, magnet sinks, right? Magnet will sink because it's heavier. So you have to mount it somehow. So put a plastic stand or something like that and keep the magnet right on the surface. Is it doable? Can you imagine this? So that's a tank of water, and that's the surface of water, and I want this magnet to be just on the surface of water. So what do? Put it on a plastic support and let it stand there. Okay? Now what do? Take a long, like knitting needle, long one, magnetize it. I showed you how to magnetize something, right? Magnetize it, and after you magnetize the knitting needle, put it into a piece of cork. Put it into a piece of cork and let it float in the water. So here is a piece of cork with the magnet needle pointing out. You understand? So this is the knitting needle's tip. Which tip? North tip. Where's the south? South is deep inside the water. So that's kind of far away to be considered existing at all, right? Make sense? So if I keep this water tub, keep the magnet in the middle, support it nicely, and then take this piece of cork and push this magnetic needle into it, and the North Pole is right there, and let it float. So if I make this float over here and leave it there, what will happen to that?
Drift to the other side,
Which way?
towards the south pole.
No, if I leave it right there, what should happen? It will just repel, because this is going to repel, so this thing is going to go this way. Right? Now what if I left it here? Will it keep going like this? Yes, it will keep go. It'll go this way, but eventually what will happen is the South Pole is pulling it also, so it will start taking a turn, and it will take a turn and go all the way boom like this. If I leave it here, what will happen? It'll go away, and then it'll take a turn. You can actually literally see this happen. If it is the water is pretty stagnant, and if you leave the magnetic needle, you'll see it kind of beginning to drift along this path. If I leave it here, it will go like this. If I leave it here, it will go like this. If I leave it here, it will go like that. Here, go like this. If I leave it here, it will go in. If I leave it here, it will go in. If I leave it here, it goes like that. What are these lines called? Magnetic field lines. You understand? So just like you had electric field lines, what's the definition of electric field line? It's an imaginary path taken by a unit positive charge when released in the field. Now, this is what happens when you release a unit north pole in the field. Again, as I said, a unit north pole does not exist, but you can simulate that to a good extent by keeping the south pole far away, right? Instead of taking a short magnet like this, if I take a short magnet like that, and if I call this unit north pole, if I call this a north pole, yeah, but the south pole is close enough, so it won't really show the difference. But if this is far away, then the focus is only on the one which is closest. So this is the pole that is closest to the magnet. The other pole is far away, and so the effect will be felt by this north pole, and it will behave like this. So you can see that this magnetic needle that you put in there in the water will start traveling depending upon where you release it. Okay, it will start moving, and which way does it move? It moves along the field. So the magnetic lines exist in that way. From where does it start? It starts from the North Pole and finally culminates in the South Pole. Do you get it? So these are the patterns that you can understand as a magnetic field lines. These are magnetic field lines. So if I release a magnetic North Pole right there, which way will it go? No, at that moment, which way is the force experienced? That way, right? So which means if I have a magnetic dipole, now sometimes it's called a magnetic dipole, two poles, because they always come like that, right? So this is so any magnet is a magnetic dipole. That's a magnetic dipole because there are two poles. So this magnetic dipole, at this point, if I'm asking what is the magnetic field's direction, it is that way, at that point. And at this point, which way is the magnetic field's direction? That way, tangent, along the tangent for that particular line. So wherever you want which direction is the electric field here? It's that way. And why is the field in that direction, even though the North Pole is here? Is because the field here is controlled by two magnetic poles. One is this strength, and the other one is that strength. So this is pushing it, and that is pulling it. So the resultant is this. You get it? At any point, the resultant. So why is the resultant in that direction here? Because this one is pushing it that way, and that one is pulling it that way. So the resultant is right in the middle. You get it? Vector resultant. So this is pushing it away, that is pulling it this way. So the resultant is going to be right through the middle, and it can be horizontal right in the middle. seeing that, come back to the Earth's magnet. So if you look at the Earth as a magnet, if you're looking at Earth as a magnet, where are the magnetic field lines starting from? Magnetic north, which is right here. So these are the field lines coming out. So if I release a unit north pole here, imagine I release a unit north pole here, which way will it go? Straight out. If I release a unit north pole here, which way will it go? Straight down. If I release a unit north pole here, somewhere slide here, so you go like that and go down. If I release it on this side, it's going to go like this. Right? If I release it a little more closer. So those are the field lines, the magnetic field lines which are already there around the Earth here. They're already existing. So tell me which way is the field line on the equator? Imagine you are on the magnetic equator. Magnetic, not geographic. See, there's a difference between the two because they are not on the same axis. Like the magnetic, this is the magnetic axis, and the geographic axis slightly out, like that. Okay? The magnetic axis, that's a magnetic, and the geographic, they're not together. In other words, the geographic north pole is not the same as the magnetic south pole, right? It's slightly off. The angle that is here between the pole, between the axis, it changes gradually. You know, it kind of fluctuates. But the angle is called angle of declination. That angle has got a special name that's called the angle of declination. The angle between the magnetic axis and the geographic meridian. Magnetic meridian and the geographic meridian. The angle between that is called the angle of declination. Yes?
So geographic is with the geographic north and south?
Yes. The geographic north and south has a different meridian, and the magnetic north and south has a different angle.
Can you repeat the definition of that one last time?
The angle between the magnetic meridian and the geographic meridian is called the angle of declination. The angle between the magnetic meridian and the geographic meridian. Meridian is the line that's running through like an axis. Okay? So the Earth is spinning about which axis? The geographic. The Earth is spinning about the geographic axis, but the magnetic axis is slightly off. Not a big angle, but it's a tiny angle. Yeah.
Isn't like one side of the magnetic field like compressed, like from the sun's like radiation and like solar flares like pushing it in?
It changes, yeah. It changes. That's why I said it fluctuates. As the Earth spins, there is fluctuation in it. The value is not the same all the time, but the fluctuation is little. Now, here, imagine you are on the magnetic equator, like here. Imagine you are on the magnetic equator. Which way will the magnetic field be? Which way? Like imagine we are on the equator right now. Okay, which way is the magnetic field of the Earth? Which direction? Huh?
Geographic north, pointing that magnetic.
No, I want the actual direction. Like you are on the magnetic equator. So if I suspend a magnetic needle right here, so that it's free to turn anywhere. So where's the north here? Which way is the north? Is that the north? What is the north? Yes. That one? Okay. So that's the north, east, east? Mm-hmm. Okay, north, south, east and west. Okay. So if I suspend a magnetic needle here, so that's free to turn in all directions, which way will it settle down? I know that way, but will it settle down like that, or like that, or like that? Which way? Yeah? If I restrict it from, let me suspend it. If I suspend it, that. I don't know if this magnet is right. But again, it can be influenced by factors such as the currents running in the, it looks like it's showing
That's
that.
just saying, north is that way.
Huh?
North is that way.
Okay, then that is right. Someone said it wrong.
Good job, man.
Let me see. Do you check that up here?
The film never does. It's west. I was like, okay, I don't know without the east end. That's it. I'm reading. I don't know which way the north is.
Yeah, the north is facing this way. I can see that here. The north is that way, and the south is that way. All right. Huh?
Looking down.
Any confusions? So north is here?
Yes, the north is that way.
Okay. Kind of confusing, right? A little bit. Let me see my compass.
Yeah. So, because I was like west, I was like, I said west that way. I was like, I know I go east too.
If I suspend a magnetic needle right here, imagine I'm on the North Pole, and I suspend this needle like this, so it's free to go. Which way will it point? I'm on the North Pole. Down, straight down. It will not settle like this. So in other words, you can't have a compass measuring anything correct. You have to basically put your phone this way to actually find the direction. Because the direction of the magnetic field is right into. So if I put a compass, the compass will actually point right down. So this is going to point right like this. It's not going to settle that way. Okay? And what if I am actually in the magnetic south, geographic south pole, and if I suspend a magnet needle, it will point straight up. Now, if I'm on the magnetic equator, and if I suspend the needle, which way will it point? Horizontal. See? Because this is horizontal with respect to the ground. So this is our horizontal, right? So when you're on the equator, this is your horizontal. And so the magnet needle also is going to face the same direction. So if you're on the magnetic equator, you put this magnetic needle, the magnetic needle will settle down absolutely horizontal, but it will in that direction. Now, are we on the equator? We're not. We are somewhere here. So which way will it point? So this is the horizontal. See, this is going to point this way. And the horizontal, with reference to this spot, is here. So the magnet needle is not going to be horizontal. It's going to be dipping down, right?
Right.
It's dipping. Can you see the dip? And as you start moving to the North Pole, the dip will become more and more. So if this is a magnet, this is how it's going to be. At this point, it's going to be like this. As I move on the earth, as I move from there, the magnetic needle is going to change deflection, see? It's changing directions. And on the equator, it is absolutely horizontal. And then it starts dipping, 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 and dips fully down. So the magnetic needle is going to dip. Can you see the angle? And the angle between the horizontal and the magnetic needle is called the angle of dip. It's called the angle of dip. So the angle here is called the angle of dip. So if I suspend a magnet, here, and if this is horizontal, this is the horizontal, and if I suspend a magnetic needle here, the magnetic needle is not going to stay horizontal. Why? Because we are not on the magnetic equator. We are in the northern hemisphere. So it's going to dip like this. And the angle between the magnetic needle and the horizontal is called angle of dip. That is called the angle of dip. So this is the direction of magnetic field. So magnetic field direction is this. So this is the magnetic field. And that is a horizontal. So the direction between the magnetic field and the horizontal at any location is called the angle of dip. Okay? So if I suspend a magnetic needle here, if I suspend, see, this is the North Pole. This is the North Pole and this is South Pole. Well, it is supposed to be the other way around. The red is supposed to be the North Pole and this is supposed to be the South Pole, but apparently somebody placed this in the wrong manner in the storage place. So this side got magnetized the opposite way. Somehow this got magnetized the opposite way. So this is the North Pole and that is the South Pole. Okay, but that's not norm. The norm is red is positive and black is negative, right? So same way here, the red is supposed to be north and this is supposed to be south, but in this case it's different. So if I suspend this like that, it's going to face the north. But if I suspend it like this, in the direction of the magnetic field, if I suspend it, all right, yeah. So this is called the dip circle. Now, why I'm keeping it like this is because I'm placing it along the magnetic meridian this way. Didn't you say that's the north and the south? So I'm placing it in that direction. And when I place it in that direction, I don't know exactly how it is, but when I place it in that direction, which way is the magnetic needle pointing? It's down. It's dipping down. How do I find the angle? It's around 52 degrees. Well, I may be wrong because I'm not placing it the right way, but we need to lock that up correctly. I need to place this in the right direction to be able to get it. So if I change this, if I'm just disturbing it, you'll see it will settle down in the right place again, the correct position. Now if I keep this on the magnetic equator region, if I take this and keep it there, which way will it face? Horizontal. That's right. It will face horizontal. See, it will finally come to that angle of 52 degrees. So we are in the northern hemisphere and it is showing that angle. You get it? So the angle right now is around 52 degrees, which is the angle of dip in this place. The more north you go, the dip will be greater. As you start moving more and more to the North Pole, the dip will become greater and greater. So if I take this and suspend it on the North Pole, like I'm placing this on the North Pole, which way will it point? Straight down. What's the angle? 90 degrees. Right? So if I place this one on the magnetic equator, it should point like this. It should point like this. You get it? So if you want to really measure the magnetic, you can actually measure the angle of dip here with the phone itself, I think. All you have to do is change the orientation of the phone. Yeah, let me try that again. Where is it? Okay. So now I know that this is the north and that's the south. So I just turn it like that in that direction. You got to position it right. I don't know. Maybe it is kind of trying to show that, but I don't know how dependable this one can be, the phone. But yes, the magnetic needle will do the right thing, okay? Because the phone is working on a different kind of sensing platform, so we don't know. Do you understand the angle of dip part of it? So what's the angle of dip at the North Pole, at the geographic South Pole or the geographic North Pole? The angle of dip is 90. So here the angle of dip is 90, and over here the angle of dip is 0. And as you move to the North Pole, the angle of dip changes. Over here it's dipping down, but here it is not dip, it's kind of facing up. Okay, so the angle is upward. So if I say take the same thing to the South Pole, not to the South Pole, but some country in the southern hemisphere, if I take it down, instead of facing it like this, instead of facing in this direction as it is doing here, it will do the other way around. Right? You understand? Yeah. So Earth has its own magnetic field, so you need to have some idea of this. Now, why we have to worry about this is sometimes they will tell you the magnetic field due to the Earth in a certain place, the actual value, and also they'll mention the angle of dip. And you may require the horizontal component of that magnetic field. Right? Now the magnetic field is symbolized by the letter B. What's the symbol that is used for electric field? E. And for magnetic field, we write B. B is a magnetic field. It's also called magnetic flux density. You'll see that later. So magnetic field is symbolized by the letter B. So if they give you the magnetic field value and the angle of dip, so if they give you the magnetic field value and the angle of dip, then you can find out if this is B, then B cosine theta is going to be the horizontal component, and B sine theta will be the vertical component, right? Because you don't know which component you're going to use in our situation. So if you need the horizontal component, then it's B cosine theta. If you need the vertical component, then it's B sine theta. Make sense? But sometimes they'll say the horizontal component of the Earth's magnetic field is this. So then just take that and go on. Because in that case, you don't require a magnetic, the dip angle of dip. Magnetic field near current carrying conductor. Magnetic field near current carrying conductors. It's current. Magnetic field near current carrying conductors. Okay. Now, we're not deriving these things. There is a law called Biot and Savart's law. We're not going into those things. We're just going straight into the equation. So you can just take the equation straight. Some of those equations are given in the formula sheet, but some of them are not. So you should be able to find out which is not and then learn it. Okay, this is required. So current magnetic field near current carrying conductors. Now you know the experiment that Oersted did, right? He took a wire, sent a current through it, right? And then he found out there's a magnetic field around it. And which way is the magnetic field? Okay, if the current is going up or if the current is coming down, which way is the magnetic field? Is it this way or that way? You know, he only saw the pattern. Strength of the magnetic field. Mu is less than 1. Not too much less than 1, like barely. Like 0.8, 0.5, something like that. You can read. Huh?
Some is still going through.
Yeah. Some still going through. In other words, this material doesn't like the existence of magnetic field through it, so it tries to push them away.
Is it material that doesn't let any of the field go through?
No, they will all let it, but it just slightly reducing. That's it. No, there's no material that's completely repelling off all the magnetic field. Yeah, you should look it up and find out which materials are common materials that are diamagnetic, which materials are para, and which ones are ferro. In fact, all these magnets and stuff like that, they're all made from ferro materials, right? That's the ferro from ferrous. It comes from there. So the strength of the magnetic field changes. So you know more about this now, right? So what if I have over here water or something like that? What will happen to this equation? You will write it as mu naught times mu r. Yeah, you'll have a mu r coming in. And then I over 2 pi. So remember that this is the permeability of the medium that is present. Now if you are thinking about air only, then it is just the same number as this. Now if you're putting a paramagnetic material around it, then we have to increase this by that factor. Okay? So you'll have mu naught times mu r into it. So the strength of the magnetic field is this. But what's the direction of it? What's the direction of the magnetic field? Now the direction of the magnetic field is given by, well, initially in different books they used to have what is known as the corkscrew rule. Corkscrew rule. Now, if you kind of say these things pretty fast, those words can, mess up, and people will understand it totally different. Corkscrew rule. So I don't like using that terminology at all. So we don't, even books sometimes they don't use that. What is a corkscrew rule? Like, the corkscrew? How do you put the corkscrew in? Which way will you turn?
Right.
To the right. So you turn it to the right to make it go in. That's a corkscrew rule. Right? Instead of that, grip rule is much easier. Grip rule. Like, here's a grip. How do you grip something? Like that, right? Which way is your thumb facing? Which way are these fingers facing? So that's grip rule. Now, how do you understand which way the magnetic field is? You grip the wire such that the thumb represents a current. Which way are these fingers facing? Inward. So the magnetic field here is backward. So which way the magnetic field is easy to find out. Right hand grip rule, write it down very clearly. Because a very common mistake from students is this. Because they are right-handed, they are writing and they're doing the test, and as soon as the grip rule comes, they take their left hand and then the whole thing messes up. It's not the left hand, it's the right hand grip rule. So make sure that is written down there and always say it the same way. I have to use the right hand grip rule and pick the right hand up. Okay? And who's left-handed here? So you're lucky. So for you, when you're doing this, you can still go with the right hand. All right, anyway, right hand grip rule it is. So how do you find the direction of the magnetic field? Use right hand grip rule. So that's right hand grip rule. So if I have a wire that is going like this, right here in this room, a wire is going like this, and the current is going down, which way is the magnetic field here? How do you find the magnetic field? If I suspend this magnetic needle here, which way will it point? So here's the current going, which way? Down. The current is going down. So what do? Take your hand, right hand, and grip it. And just coil this hand, these fingers, which way are they going? Like that. So at this point, which way will they be facing? This way. So the magnetic field will be in this direction. You understand? Yes, no? So right hand grip rule is very important. There are only a couple of rules in this whole chapter. In electromagnetism and in magnetism, there are only a couple of rules that you need to know. One of them is a right hand grip rule. And then later on, I will tell you there is a Fleming's left hand rule. That one. And then after that, after some more time, I'll tell you there's something called a Fleming's right hand rule. Okay, those are the only 3 rules that you need to know to solve any problem in magnetism and electromagnetism. Of course, there are different books giving different rules. You know, some of them come with the swimming rule. You know, people invent their own rules. But I will go with these 3 because these 3 are very common. And some textbooks actually go with different rules. I don't like, these are the 3 rules that I find students successful with. Okay? One is the right hand grip rule. Yeah. So if the current is going like that, which way is the magnetic field? Around it, like this. Do you get it? So if the current is going up in this wire, so which way is the magnetic field here? See, grip it. Now you can see which way it's going. So it's going this way. Yes.
Why would they call it the corkscrew rule if wouldn't that be the opposite of the right way?
It is not the opposite. The cork is going the screw is going which way? In.
Yeah.
And which way are you turning? See? Screw is going in and you're turning this way. Again, that's called a right-hand corkscrew rule because not all screws are right-handed screws. There are some screws which you turn and it goes the other way. You have to turn it in the opposite direction to take it out. There are some screws like that. What was it? Recently I had I was trying to take something out and it was pretty late that I realized that it was the other way around. And I was like putting all my strength into it to turn it this way to get it out. Because normally when you want to take it out, you know, you turn it the other way. So I was trying to turn, which one is that? Oh. Something. You know, when you do so many things, that's what happens. I think it has something to do with okay. Car. Something in the car. I had to apply a lot of force ultimately. By the time the nut was worn out to that extent, you know, so I literally finally had to cut it out. Oh yeah, it was not, it was the flush tank. It was a plastic nut. It was a plastic nut. You know the flush, the lever? Mm-hmm. That mechanism is held by a nut. Have you opened it at least once? No? Mm-hmm. You know, so the thing broke off. In other words, the metal rod which is inside completely got rusted and broke. And so there's no other option for me to kind of replace the whole thing. You know, the whole thing means like replace that lever mechanism. So I could get it from Home Depot for, you know, $4 or $5. I got that one, but yeah. And then when I checked this was made of plastic. What was there was made of plastic. No, it was not plastic. It was metal. It was metal. It was a metal nut getting onto it. So I have to turn it this way to turn it open, obviously. And so I put my wrench there and I was trying to turn it. And the wrench, you know, the wrench had to be big, so I had to have the big wrench. And I was gripping it and turning it. And every time I was turning it, actually was getting tighter. And I was like, what is happening? It stuck so much. So I had to kind of apply a lot of lubrication to it, but still it was not coming out. Finally, I tried with all my means, and then it didn't work out. And finally, the nut got totally worn out that I had to really cut it. I had to take a hacksaw blade and really cut it. And finally, that also didn't work. And finally, I took my drill and I drilled it and kind of broke that nut. Once I broke it, then the thing came off. And then I took the new one and I was trying to put it in and I was trying to turn it that way and it was like not tightening. I said, why is it not tightening? And then when I turned it the other way around, it started tightening up. And I said, oh my, that was a problem. So I never expected that nut will be the opposite. Anyway, now you know it. Okay, so in case you're going to open that, remember, I don't know why they keep that one that way. What's the reason for it? Oh, yeah, because when you flush it, you know, you're turning it like this. So your action should not loosen it up, it should tighten it. That's why. Your action should create a tightening effect and not a loosening effect, because if it loosens it up, like for every stroke of this way, that's the reason why they do it. All right. So there's a lot of things that are around you which you need to be aware of, otherwise you can mess things up. Okay? So I was totally not aware of it because I never, we don't replace them on a regular basis. If people are doing the job, will always know it. But I learn it by breaking some stuff. Anyway, but that was a good lesson for me. So next time I'll be alert. I'll be okay. I remember one experience of this. So I'll be. But at least it's plastic now. It was not metal. So plastic, it's easier to kind of manipulate. All right. So which way is the direction of the magnetic field? It is in. So if you have a wire carrying current and you want to find the direction of magnetic field, all you do is which rule? Right hand grip rule. That's the first rule out of the 3 rules that you're going to learn in this chapter. 3 rules only altogether. First rule is already done. You already know it. What is the first rule? If the current is this, what is this? Direction of magnetic field. Don't try to turn it the other way around. This is the natural way you turn your fingers, right? So if the current is upward, the magnetic field here is in, the magnetic field here is out. Do you understand that? Grip it. See which way are the fingers coming from here? Out. Which way are the fingers going here? In. So out is indicated by a dot. In is indicated by a cross. It's like you're seeing the back of an arrow and you're seeing the front of an arrow. Get it? You're seeing the back of an arrow and you're seeing the front of an arrow because the arrow is coming out. So the magnetic field direction is in and out. Now what about in this situation? If the current is going like this, which way is the magnetic field here, in this place? Check it out, right hand grip rule. Which way is the magnetic field here? The current is going here. Okay? So what's the direction here? In. Put your thumb in that arrow direction. Put your thumb in this direction and then keep coiling it like that. Are you okay? Yes? Oh, what? Yeah, this is indicating the direction, and so you continue the direction afterwards. Like it's only giving you a starting point, so you just continue that. You get it? This only gives you a starting point. So you put it like this, and then you can see the direction is like that, so it starts going this way. What's the direction outside? Out. Okay, now what about this current here, the same current? What's the direction of magnetic field here? In, and here it is out. What about this current here? Yeah, same, and out, and here, in, and out, and over here, in, and out. So what is the magnetic field right in the center? Which way? In, correct? The overall effect of this is in. The magnetic field is right in the center, which is in. Yep. Yep. The magnetic field is in. The direction of the magnetic field is in. So, what is this finger? Yes?
Direction of current.
Direction of current. And this one is?
Direction of magnetic.
But you know what? You can switch it. You can switch it. You know why? Because you can switch it means like, not that way. You can switch it in the sense, instead of calling this one as current, you can also have this current. So how do you do this? Find out which one is straight and find out which one is curving. Is the current curving? Is the current curving here? Then use these fingers for current. You get it? If the wire is going straight, use this finger for the current. If the wire is turning, then use this finger for the current. Which way is it turning? That way? So you just put your fingers in that same direction. Which way is the magnetic field now? What? This is turning like this. Look, my finger is over here like this.
It means out is over here.
So
Is it always pointing out? If you curling it this way, you're
No.
always pointing out.
no, the curling is this way now.
Yeah,
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 so it's
this
in.
is out though, right? Yeah, it's pointing out.
Yeah, it's always like that.
Maybe the test will be that.
Yeah, that's a magnetic field. Isn't that the magnetic field?
I don't know. I'm just gonna leave it that way.
So if this is current, this is magnetic field. And if this is current, that will be magnetic field. Vice versa.
So where your thumb's pointing out, that's out.
What do you mean out? Thumb is pointing. Thumb is pointing.
That's the direction, but like that would be out. The direction it's pointing out, right?
It's in here.
Yeah,
On
I
the
know.
board.
I know, but yeah,
What do you mean out? I don't understand the out part.
'cause that's what the dot represents.
The dot is on the outside.
Yeah.
Oh, yeah, on the
pointing
outside.
out. Yeah.
Yeah.
Sorry.